Welcome to the lecture series of Mathematical Modeling of Manufacturing Processes with subject code KME 073. I am Dr. Suman Gothwal, working as an assistant professor in the Department of Mechanical Engineering at AKGEC Engineering College, Ghaziabad. So in today's lecture, we are going to discuss about the various type of wear that can take place in the cutting tools. Then we will discuss about the Taylor's tool life equations and the problems based on the tool life. Okay. So these will be the topics that we will discuss in today's lecture. Wear of cutting tool, introduction to tool life, means what do you mean or what do you understand with the term tool life. Then Taylor's tool life equation and the problems based on the tool life. Okay. So first topic is the wear of cutting tool. So wear का meaning क्या होता है, सबसे पहले ये समझना होगा. The change in the shape of the tool from its original shape. Okay, the change in the shape of the tool from its original shape during the cutting, resulting from the gradual loss of the tool material. Okay, so this is basically the tool wear कि जो original shape है वो shape ही change हो जाती है tool की, loss of material wear out होना शुरू हो जाता है tool से material, that is the tool wear. We have seen that cutting tools are subjected to high localized stresses at the tip of the tool, high temperature, especially along the rake face, sliding the chip along the rake face. So these are the conditions or these are the factors which are responsible for the tool wear. Okay, because of the high stresses, high temperature and the over the along the rake face, जहाँ पे कि चिप जो है वो स्लाइड कर रही है, कटिंग एज जो है जो कि कांटेक्ट में आ रही है वर्क पीस के, तो वहां पर जो है टूल वियर के चांसेस ज्यादा होते हैं. दिस कंडीशन इंड्यूस द टूल वियर विच इज ए मेजर कंसिडरेशन इन ऑल मशीनिंग ऑपरेशंस. ओके, एज आर मोल्ड एंड डाई वियर इन कास्टिंग एंड मेटल वर्किंग. जैसे कास्टिंग या मेटल वर्किंग, मेटल फॉर्मिंग ऑपरेशंस में भी हमने पढ़ा है कि जैसे डाई में या फिर मोल्ड के अंदर भी वियर हो जाता है, ऐसे ही टूल भी वियर आउट शुरू हो जाता है. द टूल वियर एडवर्सली अफेक्ट द टूल लाइफ, एंड जब लॉस ऑफ मटेरियल होगा टूल से तो क्या होगा, उसकी टूल लाइफ जो है वो अफेक्ट होनी शुरू हो जाएगी, क्योंकि उसकी स्ट्रेंथ जो है वो कम हो जाएगी. टूल की ज्योमेट्री चेंज हो रही है, टूल की ज्योमेट्री मॉडिफाई हो गई है, तो इट विल अफेक्ट द लाइफ ऑफ द टूल एंड द मशीनिंग ऑल्सो. ओके, जैसे कि कटिंग फोर्सेस इंक्रीज हो जाएंगे, जो सरफेस फिनिश की क्वालिटी है वो भी चेंज हो जाएगी. Okay, poor surface finish we will get here. So the tool wear adversely affect the tool life, the quality of the machine surface and its dimensional accuracy also. Okay, and consequently the economics of the cutting operation. So these tool wear are not favorable. Okay, तो हमें क्या करना होगा, हमें जो है वो फैक्टर्स देखने होंगे जिसके थ्रू कि we can reduce the tool wear. Okay, and the corrective actions we have to take. So we can see in this diagram that this is our tool. Basically we are talking about the single point cutting tool, and this is the rake surface. Okay, so rake surface or the rake face is the face over which the chips will slide or chip will flow. So you can see here, this is the chip flow direction, this is the rake face, this is the crater wear. Okay, different types of wears are there. So in the coming slides we will discuss all the wears, all the tool wears one by one. So we can see here that this is the crater wear. So crater wear क्या है, pit formation type जो है यहाँ पर हो गया, pit formation हो गई है, and this is along the rake surface of the tool. Okay, then this is the nose radius यहाँ पर provide हुई है, this is the nose, and this is the flank surface of the tool. ठीक है, रेक फेस से जो वर्टिकल सरफेस होता है that is the flank surface of the tool. So we can see here that along the flank surface the flank wear will take place. This is the second type of wear. First one is the crater wear, which will be along the rake surface of the tool, and the second one is the flank wear, which will take place along the flank surface of the tool. And here we can see this is basically the main cutting edge. We have seen that side cutting edge and cutting edge. So side cutting edge and end cutting edge है, so this is the main cutting edge. Okay, and we can see here that there is a V shape formation has taken place along the vertical surface, means along the flank surface of the tool, and this is known as the notch wear. Okay, this is the notch wear. So we can see in this diagram that here the loss of material is taking place. So this is along the vertical surface of the tool, vertical surface and the rake face also. So these are basically the example of the crater and the flank. Flank में ये ज़्यादा है, लेकिन यहाँ पे अगर हम देखें तो यहाँ पे थोड़ा सा आपका रेक सरफेस पे भी मटेरियल लॉस हो गया. Okay. Now we will discuss all the tool wear. So first one is the crater wear. So the chip flow across the rake face of the tool, resulting in severe friction between the chip and the rake face, and leaves a scar over the rake face, which usually parallels to the major cutting edge. Okay, as we have discussed earlier also, okay, after the deformation, the deformed material will slide over the rake surface of the tool, and because the friction will take place at the interface between the tool and the underside of the chip, तो यहाँ पे scarf formation जो है वो हो जाएंगे rake surface पे. Okay, the crater wear can increase the working rake angle. So इससे क्या होगा, क्योंकि rake surface पे crater formation हो रही है, तो rake angle जो है वो increase हो जाएगा, and it will reduce the cutting forces को ये reduce कर देगा, but it will also weaken the strength of the cutting tool. rake face जैसे जैसे increase होता रहेगा तो strength जो है tool की वो कम होती रहेगी. Okay, so these are some of the diagrams which are showing the crater wear. So in first one we can see here, so this is the rake face. So we can see here कि यहाँ पर जो है chip flow हो रही थी, उसकी वजह से यहाँ पर ये pit formation हो गई है, crater wear आ गया. This is the V shape on the flank surface. This one is the flank surface. So यहाँ पर loss of material है. This is along the nose. So it is also known as the nose wear. This is along the flank. So it is known as the flank wear. And this is the V formation. तो यहाँ पे notch wear हो जाएगा. Clear? This is the basic diagram that crater wear is taking place here, where the secondary deformation zone is present, and this is like this, or the rake surface of the tool, and this is the flank surface. This one is the flank surface. So here the flank wear is taking place. Clear? So in this diagram we can see here, this is the rake surface. So here the loss of material is taking place. So this is basically the crater wear, and this is along the flank surface. So here the flank wear is taking place. You can see in this diagram also. Clear? Now we come to the flank wear. Okay, so flank wear will take place along the flank surface of the cutting tool. The wear on the flank or the relief face is called the flank wear, and it results in the formation of a wear land. Okay, wear land की formation हो जाती है. Wear land formation is not always uniform along the major and minor cutting edges of the tool. So there are two type of cutting edges are involved, minor cutting edge or the major cutting edge. तो ये flank wear जो होगा, this will not be uniform along these two cutting edges. The flank wear most commonly results from abrasive wear of the cutting edge against the machine surface. Okay, so flank wear कहाँ पर होगा, ये किसकी वजह से होगा, abrasive wears की वजह से. ठीक है, of the cutting edge against the machine surface. The flank wear can be monitored in production by examining the tool or by tracking the change in size of the tool or the machine part. So flank wear जो है इसकी हम monitoring कर सकते हैं, हमें पता चलेगा कि कब हमें tool को replace करना है, कैसे, या flank wear जो है वो होना चाहिए, हमें क्या करना पड़ेगा, tool को monitor करना पड़ेगा, machine surface को monitor करना पड़ेगा. Clear? And flank wear can be measured by using the average and maximum wear land size. Wear land size को अगर हम measure करेंगे तो उससे हम flank wear जो है वो determine कर सकते हैं. तो these are the diagram, same diagram है. ये cut CFD is chip flow direction. This is the crater wear or the rake face. Flank wear फ्लैंक सरफेस पे है और ये नॉच वी टाइप की फॉर्मेशन हो रही है. दिस इज द नॉच वियर. ओके, सो दीज आर दी, you can see the flank wear along the vertical surface. This is a built up edge formation. मतलब after the workpiece material is reformed, it is depositing of the cutting edge. Okay, और tip of the tool पे ये deposit होना शुरू हो गया है और यहाँ पे इसने built up edge की formation कर दी है. ठीक है, so it will act as the false cutting edge. You can see here also this is the basically the flank wear and this is the crater wear. Now we come to the notch wear. Notch wear में क्या होगा? This is a special type of combined flank and the rake face wear. ठीक है, तो ये जो है आपका थोड़ा पार्ट इसका रेक फेस पे होगा और थोड़ा जो है वो फ्लैंक सरफेस पे होगा. तो ये जो है कंबाइंड होती है फ्लैंक और रेक फेस वियर का, विच अकर्स एडजेसेंट टू द पॉइंट वेयर द मेजर कटिंग एज इंटरसेक्ट विद द वर्क सरफेस. सो ये इसका मेन एरिया होगा जहाँ पर कि नोच वेयर होगा. The gashing or the gouging at the outer edge of the wear land is an indication of a hard or abrasive skin on the work material. Such a skin may develop during the first machine pass over a forging, casting or hot rolled workpiece. It is also common in machining of materials with high work hardening characteristics, including many stainless steel or heat resistant nickel or chromium alloys. So these are the materials or these are the conditions जहाँ पे कि notch wear formation के chances high होंगे. Okay, so we in this diagram we can see the notch formation like this. तो यहाँ पे ये crater wear का भी part है, flank का भी है और यहाँ पे V shape की notch formation हो रही है. Same you can see in this diagram में यहाँ पे notch wear form हो रहा है और यहाँ पे notch wear form हो रहा है. Clear? Now we come to the tool life. Okay, so tool life क्या होती है? टूल लाइफ को कैसे डिफाइन करेंगे? द अमाउंट ऑफ सेटिस्फैक्ट्री परफॉर्मेंस और सर्विस रेंडर्ड बाय ए फ्रेश टूल और ए कटिंग पॉइंट टिल इट इज डिक्लेयर्ड. तो यूजफुल लाइफ ऑफ द टूल इज बेसिकली द टूल लाइफ. ओके, जब तक टूल जो है वो प्रोडक्टिव रहेगा, जब तक टूल जो है वो फेल नहीं होगा, जब तक टूल जो है जिस परफॉर्मेंस के लिए उसको डिजाइन किया है वो परफॉर्मेंस दे रहा है. दैट इज द यूजफुल लाइफ ऑफ द टूल इज द टूल लाइफ. Wear and hence tool life of any tool for any work material is governed mainly by the level of machining parameters. Okay, तो अब टूल लाइफ भी बहुत सारे फैक्टर्स पे डिपेंड करेगी कि उसकी वर्किंग एनवायरनमेंट, कौन से वर्किंग एनवायरनमेंट्स में हम उस पर्टिकुलर टूल को यूज कर रहे हैं. फॉर एग्जांपल कटिंग वेलोसिटी, फीड, chip thickness, tool geometry, material of the cutting fluid, rigidity of the machine and the depth of cut. So these are the parameters which affect the life of the tool. Tool life obviously decreases with the increase in the cutting velocity and keeping other conditions unaltered. Okay, तो अगर हाई कटिंग स्पीड पे टूल को यूज करें तो उतना ही ज़्यादा टेम्परेचर होगा, उतना ही ज़्यादा वियर आउट होगा. तो मतलब कि हमारी जो टूल की लाइफ है वो डिक्रीज हो जाएगी. नाउ वी कम टू द टूल लाइफ इक्वेशन. सो वन ऑफ द इक्वेशन दैट इज द टेलर्स टूल लाइफ इक्वेशन जो कि हम यूज करते हैं. When F.W. Taylor's plotted taking both V and T in long scale, a more distinct linear relationship appear. With the slope n and intercept c, Taylor derived the equation as v into t to the power n is equal to c. This is the equation which is known as the Taylor's tool life equation. N is basically the Taylor's tool life exponent. Okay, and the values of both n and c depends mainly upon the tool work material and the cutting environment or cutting fluid applications. Okay, c is your constant, n is your Taylor's tool life exponent. Okay, v is the cutting velocity and t is the tool life. Okay, these are the factors which are involved here. So the value of N or C will depend on cutting environment and tool work material. So for example, if we talk about the HSS, the value of N will be 0.125. कार्बाइड्स के लिए N की जो वैल्यू होगी that will be 0.25. N is equal to 0.5 for the coated carbide or ceramics, and C is a constant which is given for the workpiece material. And we have, okay, in this Taylor's tool life equation, we can see here that the tool life is depending on the cutting speed, okay, and the value of N only. Okay, but various factors are also involved, like the depth of cut, feed, they are also affecting the life of the tool. बट यहाँ पर जो है केवल इन एन पे नंबर ऑफ ईयर्स के लिए, जितने ईयर्स के लिए हम टूल को यूज कर रहे हैं, यहाँ पे जो है कटिंग स्पीड कौन सी यूज कर रहे हैं, इस पे ही हमारी टूल लाइफ डिपेंड कर रही है. सो ए मॉडिफाइड टूल लाइफ जो है वो हमने ड्राइव की काफी रिसर्च के बाद. तो यहाँ पे जो है मॉडिफाइड अगर टूल लाइफ देखें तो दिस इज द मॉडिफाइड टूल लाइफ, मीन्स v into t to the power n, f power n1 and d to the power n2 is equal to c. Now it will give the more effective results, more accuracy, because it is depending on the cutting speed, the feed and the depth of cut also. Okay, so ये यहाँ पे डिपेंड कर रही है. तो यहाँ पे जो है हमें ज्यादा एक्यूरेट रिजल्ट मिलेंगे टूल लाइफ के लिए. Now we will see one problem which is based on the tool life. So the problem is the total life of a HSS tool is expressed by the relation V into T to the power 1 by 7 is equal to C1. And for tungsten carbide, तो दो टूल हमें दिए हुए हैं, HSS tool and the tungsten carbide का tool. वहां पे हमें tool life equations given है. If the tool life for a cutting speed of 24 meter per minute is 128 minute, compare the life of two tools at a speed of 30 meter per minute. Okay, so here what is given, सबसे पहले हमें दिया हुआ है HSS tool, clear, and the second one is the tungsten carbide tool. Two tools are given. For HSS tool, the relation is V into T to the power 1 by 7 is equal to C1. And for this, V into T to the power 1 by 5 is equal to C2. Okay. Now, here the cutting speed is given. Means the value of V is given as 24 meter per minute, and tool life is given tool life is 128 minutes. Okay. Now we want to compare the tool life of these two tools at a cutting speed of 30 meter per minute. So how we will do this? First, we will put the values here in this equation. T is here 128 to the power 1 by 7 is equal to C1. And here we will do 24 128 to the power 1 by 5 is equal to C2. Okay. So after solving this equation, we will get the value of C1 and C2. So after solving this, we will get the value of C1 as 48. And after solving this, we will get the value of C2 as 63.33. Okay. Now, we want to compare the value of or the tool life at the speed of 30 meter per minute. So what we will do? Now for V is equal to 30 मीटर पर मिनट, तो टूल लाइफ इक्वेशन क्या हो जाएगी, V into T1 for first tool equation is 1/7 is equal to C1. C1 is your 48. So यहाँ से क्या होगा, और V की वैल्यू कितनी है 30, तो यहाँ पर आ जाएगा 30 into T1 to the power 1/7 is equal to 48. So we will get T1 as 26.84, or we can say it as the 27 minutes. Clear? Now we will do it for the V will be same for this. Okay, so we will put the value V into T2 to the power 1/5 is equal to C2. So V is 30 into T2 power 1/5 is equal to 63.33. Okay, so we will solve it for T2 and we will get it as 42.5 minutes. Okay, so this is the tool life for, this one is the tool life for the HSS, and this is for the tungsten carbide. Okay, now the question is to compare the life of the two tools. Okay, so we want to compare the life of two tools, so we will do T2 by T1. Okay, so T2 by T1 is basically 42.5 divided by 27. Okay, so T2 is 1.57 T1. Okay, this is the comparison of these two tools at a speed of 30 meter per minute. Okay, so in this way we can solve the problems based on the tool life. So that's all for today's lecture. So in today's lecture we discussed about the Taylor's tool life equation, various factors over which the tool life will depend, the problems based on the tool life, and the various type of wears that can take place in the cutting tool during the cutting operations, and how they affect the machine quality, how they affect the life of the tool. So thank you very much.